Hello, everybody. Is it weird that I live stream so often now that I sort of like forget that I'm on camera, and like sometimes I'll be sitting here and I'll literally almost forget that I'm live and that I have a class to teach. I just start daydreaming and thinking about something else. And maybe one of these days I'll just forget about everyone. Wait for a couple more people. All right. So, we're going to do the review of the last content that we covered this semester. And so we started out with rotational dynamics. Okay, so this is going to be the first topic of review for today. So the first concept was the concept of torque. Okay, and torque is equal to F perp times R, where you have some blob and there's a pivot point on the blob, and you apply a force maybe right here like that. So there's the force that you apply. So you draw a a line from the pivot point to where the force is applied, and the length of that line is r. And then once you've drawn that line, you have a component of the force that is perpendicular to the line and a component of the force that is parallel to the line. And so from trigonometry, you get the perpendicular component, and that's how you calculate torque. It can be clockwise or counterclockwise. Counterclockwise is considered positive, clockwise is considered negative. All right. So most of the time, these forces might be applied forces. Okay. However, sometimes the force is gravity. So gravity can exert a torque. And so the torque due to gravity, what we do is, let's say that the center of mass is right here. So this is the symbol for center of mass. Okay. And so you have, you draw a line from the pivot point to the center of mass, which I called RCM. And then the weight force is mg. And so I can see that part of that weight force is perpendicular to the line connecting the center of mass to the pivot point. And so the torque due to gravity is the perpendicular component of mg times RCM. Okay. So how do we calculate RCM or XCM? So there are kind of two ways to do it. You can calculate the center of mass from just summing up xi times mi over m tot. Okay, so this is the discrete way if you have a discrete collection of masses. But if you have a continuous distribution of mass, then you need to do the integral of lambda of x times x dx. So remember, lambda is the linear mass density divided by the total amount of mass is going to be the integral of just regular lambda of x dx. So not lambda of x times x, but just lambda of x. Okay? So that's how you get the center of mass. We also talked about the inertia. Okay? And so the inertia is, so this is inertia, this is torque. The inertia measures how difficult it is to rotate something, and it's the sum of mr squared, miri squared, where r is the perpendicular distance from the axis. Okay, so this is, again, the discrete definition of inertia, but if we have a continuum distribution of mass, it's going to be the integral of lambda of x times x squared dx. So what was I going to say? We learned kind of an important theorem. It's called the parallel axis theorem. Okay, and so let's say you have a blob, and here's the center of mass of the blob. And so you have an axis of rotation that goes through the center of mass. Okay, so there's going to be a certain inertia associated with that axis of rotation. And if you have a parallel axis that is offset by an amount d, then what the parallel axis theorem says is that the inertia about this axis is equal to the inertia about the center of mass axis plus md squared. Okay, so that is going to show up several times on the final. So make sure you understand that, the parallel axis theorem. Okay, so that is inertia. And then we learned Newton's second law for rotation. Okay, and Newton's second law for rotation says that net torque equals I times alpha, where alpha is the angular acceleration. So we have theta, which is the angular position. We have omega, which is d theta dt, which is the angular velocity. And we have alpha, which is d omega dt, or d2 theta dt squared. That's the angular acceleration. So we can calculate that from the torque and the inertia. So if alpha is constant, then we get equations of angular kinematics, which are identical to the equations of linear kinematics. So there was delta theta equals omega naught t plus 1/2 alpha t squared. There was omega final equals omega initial plus alpha t. And there was omega final squared equals omega initial squared plus 2 alpha delta theta. All right. So then we went on to talk about static equilibrium. Okay, and static equilibrium is when an object is not rotating or translating, and that means that the net torque is equal to 0, and it means that the net force is equal to 0. Okay, so this results in a system of equations that you will use to solve whatever you need to solve for. Okay. Sometimes, if an object is not in equilibrium, it might be rolling. Okay, so we talked about rolling. And if something is rolling, you have net torque equals I alpha. You have net force equals ma. And then you have this equation that expresses the fact that it's rolling without slipping, which is that alpha over r equals linear acceleration. Okay, so this is a system of equations that you can solve for the linear acceleration. Okay, we talked about energy while rolling. Okay, so in general, the total amount of kinetic energy you have is equal to the translational kinetic energy, which is 1/2 mv squared, plus the rotational kinetic energy, 1/2 I omega squared. If you are rolling, omega is equal to v over r, and so you can simplify the equation for kinetic energy if you are rolling to 1/2 mv squared times the quantity 1 plus I over mr squared. Okay, so you can use that to solve these problems in terms of energy. You might have, again, translational kinetic energy. For example, a block, because it's rectangular, typically has translational kinetic energy, but not rotational. Okay, something like a pulley could have rotational kinetic energy, but not translational kinetic energy. And some things like a wheel have both. Okay, so for things like a wheel, you would apply the rolling kinetic energy formula. Thank you. Yeah, you're right. A equals alpha r. Look out. Yeah, so I wasn't thinking, but if you think about it, linear acceleration is meters per second squared, so it has to have something with units of meters on the numerator. So that's why r is in the numerator there. If you are calculating the potential energy of an extended object, that is going to be mg y cm. So if you have an extended object, the potential energy is calculated using the elevation of the center of mass. Okay, and there's a nice little equation that we learned, which is if you have an extended object, okay, and it's pinned, and here's the center of mass, and this angle is theta. We learned a nice equation that is YCM equals, and that we'll call this distance L, L times 1 minus cosine of theta. All right. Then we talked about angular momentum. If you have an extended object that is spinning, the angular momentum is I omega. So this is sometimes called the spin angular momentum. If you have something like a tether ball that's going around a point mass, essentially going around in a circle, then the angular momentum is mv per r, and that is sometimes called the orbital angular momentum. The total amount of angular momentum before is equal to the total amount of angular momentum afterwards in the absence of torque. Okay. So then we talked about SHM. So simple harmonic motion. So what I showed is that the equation of simple harmonic motion is minus omega squared times the quantity x minus c equals acceleration. So if you can put the equation into this form, then the particle that experiences this equation of motion will undergo simple harmonic motion. Okay? About C, which is called the equilibrium point. So this is position. This is the equilibrium point. This is a constant depending on the properties of the system. And A is, of course, the acceleration. Okay, so if you have this equation, then your position as a function of time is going to be C plus A cosine of omega t plus phi. Okay, so C and omega are determined by the equation of motion. All right. A, which is called the amplitude, and phi, which is called the phase, they depend on how the system is disturbed. Okay, so they are more or less, they're called initial conditions. And they depend on how was the system disturbed. So was it given a big disturbance or a little disturbance? When was it disturbed? Etc. Okay. Omega is related to the period. So the period is 2 pi over omega. So basically, if you are able to write the equation of motion, okay, the equation of motion is going to tell you omega, which tells you the period. So writing the equation of motion is equivalent to knowing what the period is going to be. All right. And we analyzed a couple of systems. So there was the mass spring system. Okay. There was, and so for a mass spring system, we put the equation of motion in the standard form, and what we found is that the period is 2 pi square root of m over k. We also studied a physical pendulum. Okay, and a physical pendulum, I see this and I just think Pickle Rick, because I just watched the Pickle Rick episode of Rick and Morty yesterday, which supposedly is a famous episode. Pretty good. So for a physical pendulum, it's just a blob. There's a center of mass somewhere. Okay, so you have some inertia rotating about the pivot point. You also have some RCM. And so the period of a physical pendulum is equal to 2 pi square root of I over mg RCM. Okay. One thing I want to point out is that this inertia is often calculated with the parallel axis theorem. Okay, so beware of that. We also talked about the ubiquity of SHM, which is basically the idea is if you have a U of X graph, okay, the potential near the equilibrium point looks like a parabola. And if your potential looks like a parabola, then you have simple harmonic motion. So for small oscillations, so I'm going to put SO for the period of small oscillations about an equilibrium is 2 pi square root of m over u prime prime of evaluated at the equilibrium point. Okay? So then we talked about energy in the mass spring system. Okay, so the energy in a mass spring system is 1/2 mv squared plus 1/2 kx squared, which could be written as, depending on where in the motion it's evaluated, it could be written as 1/2 mv max squared. It could be written as 1/2 ka squared, where big A is the amplitude. All right, so we use that to analyze problems. So I think that's about all we did with the mass spring system. And then we did have one sort of random lesson about power. Okay, and so power is the rate at which work is done. And so I derived an equation for power that was F dot V, the dot product. And then I also talked about rotational power, which is torque times angular velocity. All right. So anyways, that is the review. I don't think I forgot anything. So I will see you in the Zoom room for a quick check-in, and then I'll probably let you guys go early. Okay? So see you soon.